Welcome back to ECE 442-542. Again, if you're an online student, make sure you know which way you're going to take the exams, either through Examity or with a proctor. And you might be thinking about, if you haven't already, completing homework number 1. That's due on Monday, and it's maybe a little bit of a stretch. Some of the material on homework 1 may not be explicitly covered in class, and I'm trying to get you to make sure you're connecting with the material in its more global sense. And homework 1 is really designed in a way that when we start talking about systems in subsequent parts of the class, you'll have a better feel for where these systems, where these G of S's, where these G of Z's might originate. I don't see how this applies. Or what does a state space representation really mean? Well, now you have to find one for an electrical circuit. At least you have some connection with reality on these concepts or topics. Again, if you want a little bit more background, there's plenty of reading material that is available to you. And in terms of block diagrams, I think it's the section 5s in chapter 1 and chapter 2 of those discrete time system foundation notes that might be helpful. We're going to talk about block diagrams today, creating one from a difference equation. Then we will actually create a transfer function from a block diagram. I want you to feel comfortable going in and out and around and up and above in different ways of connecting difference equations, differential equations, block diagrams, transfer functions. I want you to get comfortable with those interrelationships. We'll look at then, once we have a system in block diagram form, and in particular if it's an all delay block diagram, we can then immediately create or generate a state space representation from the block diagram simply by assigning the outputs of those delay blocks as our state variable components. And we'll go through that today. Then we'll talk about how this state space representation has a system matrix, a phi matrix, that's related to the A matrix for a continuous time system state space representation. Here in discrete time, notation-wise, I will call it phi. We'll see that the eigenvalues of that phi matrix are consistent with the poles of our system in a transfer function description. We're trying to interrelate all of these different ideas. Then we'll look at, if somebody gives you a all delay block diagram, can you turn that into the frequency domain? And that's a fairly straightforward process. You simply replace the delay blocks in the time domain with operators of z to the minus 1. Now your signals need to be in the frequency domain, but you now have a frequency domain block diagram that you can use to find transfer functions. We'll then talk about what is this z variable, and I'm assuming you've played with S a lot and know that that's a complex frequency, or it's a complex number, and z is likewise a complex number. They are not the same, but they are related, and we'll show how to map between the S domain point or location to its representative location in the z-plane. That's probably as far as we will get, but in anticipation of getting further, you need to understand these relationships of sampling frequency, which we may refer to in radians per second, omega sub s, or in hertz as f sub s, and those are related by this 2 pi. 2 pi f is equal to omega, and the sampling frequency in hertz, f sub s, is reciprocally related to the sample period, capital T. If you are given a continuous time system and you want to find its discrete time equivalent, you'll need to pick a sampling frequency or a sample period. The sample frequency, omega sub s, here in our rule of thumb, we'll say, oh, that needs to be 30 times the frequency in the continuous time system, so that we capture representative information. You've maybe heard of the Nyquist frequency, where you sample at twice the highest frequency. We're in a controls class. We want more than just Nyquist. We're going a little extra. We need to do 30 times so that we have more information in our waveforms that we are looking at. Then we will get into going from a difference equation into a frequency domain representation by this operation of z to the minus 1, or their powers of z to the minus 1, and that naturally then leads us into, oh, can we do or find a z transform relative to how you've now found a Laplace transform? How do we now take this sequence of numbers that we are representing as x, little x of n in this expression, how do we create a frequency domain transform representation of that time sequence of numbers? And that's the z transform. That's where we're headed. Now let's step back and go through creating an all delay block diagram from a difference equation. Somebody may hand you a difference equation and they may say, can you give me a state space representation for that difference equation? One way to do that is to first put this difference equation into an all delay block diagram, and then it's very automatic to convert that block diagram into a state space representation. The first step then is to convert or express or create an all delay block diagram that behaves just like this difference equation does. And that gives you now a graphical way of thinking about this dynamical relationship between a signal, W of n, and a forcing function, R of n. We're exciting this system that we're writing in terms of W. It has some delays. What's the order of that system? Second order, because we have two delayed terms, and we're forcing it with an R of n. An R of n could be any arbitrary signal. The process that we will use to create this all delay block diagram is first to rewrite that difference equation as the second line states. We're going to solve for the highest value of our index in time. In this case, that's W at time n. And we push all the other terms on the other side of the equality. And if we're anticipating what we're going to do, this will actually be how we will create signals relative to a summing junction. The output of our summing junction will be W of n, and it's going to now have three signals going into it. An R of n signal, a delayed omega signal, and a double delayed omega signal with gains associated with them. But right now you know that we need two delay blocks because it's second order. So now you can just put those on your paper, your delay blocks, and say, I know I need two. And what we are now wanting to do is figure out how do we interconnect these delay blocks with gains and summing junctions to be equivalent to that difference equation that's still on the top of our paper. And the first thing that we may do then is put in a summing junction. And consistent with what I suggested, let's now say the output of that summing junction is in fact W of n. And the output of that summing junction is because the arrow is going out of the circle that's representative of the summing junction. Going into that summing junction, the inputs to that are the three signals on the right in that difference equation. We have an R of n, and that's something that we have the ability to specify, so that just goes in directly. That's R of n. But now we need to create two more terms, and right now this is a fairly straightforward process because this difference equation's not that involved. If I take Wn as an input to a delay block, what comes out of the delay block? It's W of n minus 1. It's one delayed version of what was on the input side, which was W of n. Coming out then of that delay block is this W of n minus 1, and in fact we can use that as the input to the next delay block, and now we know coming out of that delay block is a one sample period delayed version of what went in, which in terms of the original W signal is W of n minus 2. We now have all the signals available that we need to produce W of n. We first need to take W of n minus 1, scale it, and now I'm looking at that term, scale it by 3, and I'm going to scale it by minus 3 so that all my signals going into the summing junction have positive signs. Or I'm now going to say, oh, I have a minus 3 for a scaling factor or for a gain. I'm going to take as its input W of n minus 1, and the output of that is really the minus 3 W of n minus 1 that I was trying to use as my second signal as an input to that summing junction. To finish it up, now we take minus 2, and that's going to be used to scale W of n minus 2, and that will now be our last, and now that minus sign is a little close to the edge, so let me make sure that it's clear, and that's now a block diagram representation of the original difference equation. We can now tweak that block diagram with whatever signal we're interested in. R of n is some sequence of numbers. We can push those in, and out coming from the summing junction will be the behavior of W of n. That solves that difference equation. But once we have it in this form, now we can actually create a state space representation. Now that we have this block diagram, we can label it in such a way that we can produce a state space representation. And if we're looking at a state space representation, can we anticipate some features or properties of that state space representation? And by that I'm meaning, how many state variables do you anticipate? 2. It's a second order system. We would expect 2 state variables, and we'll just call those x sub 1 and x sub 2. And if we label or use, here's our strategy to create a state space representation, is assign state variable components to the outputs of each delay block. And to be consistent with what I've anticipated, let me just call this far right signal x sub 1 of n. That's one of my state variable components. The other state variable component is the output of the first delay block, and I'm going to label that as x sub 2 of n. That now gives me what I need to create my state space representation, but I also need to realize that this signal is not only called x sub 2 of n, but it's also related to x sub 1 of n. What is it in terms of x sub 1 of n? If the output of that delay block is x sub 1 of n, what's the input to that delay block in terms of x sub 1? So now the input of that needs to be something such that when it's delayed by one step, it produces x1 of n. What do I need to now put in as an input in terms of x1 so that when I delay it by one sample period, the output is x1 of n? It now needs to be x sub 1 of n plus 1. That's also this signal that I'm labeling here. This is now x sub 1 of n plus 1. And that's actually equal to x sub 2 of n. And we're going to use that information in our state space representation. That's the same signal. X sub 2 of n is exactly the same by the way that we've labeled this diagram as x sub 1 of n plus 1. And we need to find, for our state space representation, equations for x1 of n plus 1 and x sub 2 of n plus 1 in terms of x1 of n, x2 of n, and r of n. If that's now x sub 1 of n, what is this signal in terms of x sub 2 of n? Everybody okay with where those labels came from? I create this all delay block diagram, and then boom, the process is just label the outputs of the delay blocks as state variable components. If I now had 6 unit delay blocks, I would be expecting a 6th order state space representation. And I would have 6 state variable components, x1, x2 through x sub 6. Here I just have 2 delay blocks. I have an x1 of n and an x2 of n as the outputs. The inputs, now I know what they are in terms of x1 and x2. Now can I fill in these equations? The structure needs to be a state variable component at time n plus 1 in terms of state variable components at time n and inputs at time n. And our only input was r of n. I now need to figure out what these coefficients are such that I produce x1 of n plus 1. So I go back to my state variable, or my all delay block diagram, and I say, okay, what produces x sub 1 of n plus 1? Well, I don't know if I should. Let's just concentrate on this, but now I'm going to mess it up here. If I had a summing junction there, I could have more going into that summing junction maybe than just x sub 2 of n. I could have a u, I could have an x1 of n. Do you see that I could maybe have something coming there with a gain? I could maybe have something here with a gain going into that. Boy, I'm making a mess. But it's highlighted, so you can filter that out. And it's a, boy, that's a poor highlight in terms of visibility for me. But you have young eyes, you can see that. I can't even see you in the room, so I just assume I have 100 students in here. Wow, I have an optimistic filter on today. But for this example, do you see what I'm trying to suggest with the highlights? That x sub 1 of n plus 1 would be the output of that summing, that yellow highlighted summing junction, and it could have many different combinations of x1 of n, x2 of n, and r of n. In this case, it does not, and now I'm playing with fire. And I didn't even get burned yet, so let's just leave it at that. Yes, question? You want me to put the highlight back on?
Would you say that x2 of n is equals to x1 of n plus 1 then in this example?
So now what is x1 of n? Let me just write it here. x1 of n plus 1 is equal to, I need this to be a linear combination of x1 of n, x2 of n, and r of n. In this block diagram, what does it tell me x1 of n plus 1 is equal to? It's too straightforward. It makes it hard. But it's exactly the same signal as x sub 2 of n. That's all it is. In this particular system, x1 of n plus 1 is in fact that. Was that your question? There's your answer. Now we need to just put that into this structure. How do we do that? How much x1 do we need? 0. How much r do we need? How much x2 do we need? There is our first order difference equation, and it's coupled. It has x1 of n's, x2 of n's, and r of n's in it, but that's the structure of our first equation in our state space representation. The next one, x sub 2 of n plus 1, that gets a little bit more interesting. Am I going to mess you up if I kind of write it here? What is x sub 2 of n plus 1? I now need to write that in terms of x1, x2 at n, not x1 of n plus 1, but x1 of n, x2 of n, and r of n. But that's available to us. What is x sub 2 of n plus 1? To make it consistent with how I'm going to write it below, how much x1 of n is present? Isn't it minus 2, x1 of n? How much x sub 2 of n? Minus 3. And is there any r? Plus 1. There are coefficients that we need in this state space representation here. I now say, oh, that's minus 2, this is minus 3, and this is 1. And did I even define an output? I didn't, so let me just define one. Let me just say that our output is right here. That I'm just assuming that that's my output. I could have made my output some linear combination of x1, x2, and r. But here, not to mess things up too much, let me just say that signal coming out of the rightmost delay block is what I'm going to consider my output. Your output could be something that you want to monitor or keep track of, or it could be something that you physically measure in your system. It could be a measurable signal. It could be something that you create because you want to monitor it. And you say, this is what I'm interested in. Here's my output. Here I'm just going to say, let's let it be that. If that's the case, what is y of n in terms of x1, x2, and r, those three at time step n? This has no dynamics. It just has a linear relationship between x1 of n, x2 of n, and r of n. What is y of n? Again, this one's too easy that it's hard. This is just x1 of n. But do you see that I could have, I don't know why I'm doing this, I could have had a summing junction, and I could have taken some of this and put it in there. I could have taken some of this and put it in there, and there's my output. And I could have had a gain here, and it would have been a different linear combination. Question. How do I determine the gains that are in this block diagram? Or in these highlighted? So in the highlighted, that would depend on actually what you need it to be. So it would depend on either your particular output. It might be a sensor that you have, and the sensor, for whatever reason, takes 3 of x1 and combines it with 7 of x sub 2 to produce y. And that would be your gains in those boxes. Here, I'm not making it that complicated. I don't even have these highlights present. I've just said okay, my heart rate's high now, but I've just said my y of n is equal to x sub 1 of n. Doesn't take much to get my heart rate going, does it? No drugs involved, just highlight. What is y of n then? Pretty basic. Now we want to put this in a matrix form. And do you see the structure of the matrix form? I've already put it in play, but this system matrix, which is what I'm calling this matrix, needs to be square. It needs to have as many rows as it has columns to be compatible with this representation. What's in the first row of this 2 by 2 capital phi matrix? Zero, 1. What's in the top row of my input matrix? This is what I'm calling my system matrix. This gamma is my input matrix. What's the top entry? This input matrix, what are the dimensions on gamma? How many rows does it have? 2. It has to be compatible with the left-hand side, which has 2 rows. Gamma has to have 2 rows. How many columns are in gamma? 1. There's only 1 input. If I had 2 inputs, then gamma would be 2 columns wide. I only have the single input, and what's the top row of gamma? Zero. Are we comfortable with where those coefficients came from? We're simply rewriting those difference equations in a matrix form. And now we can fill in the second row of both phi and gamma. Minus 2 minus 3. And gamma has a second row of 1. What do I put? Now this matrix is my output matrix. Let me just say that's going to be H. And my direct feed-through matrix here, I'll say is J. What are the dimensions of H? I only have 1 output in this example. On your homework, you actually have a 2 output system in, I don't know, problem 3 maybe. Is that the state space problem? So you actually, in that problem, you have how many, in problem 3 of homework 1, How many state variables do you expect to have? I hope people have looked at it. How many energy storage elements are there? There are 4. There's 2 inductors and 2 capacitors. You're expecting a 4th order state space representation. And I'm identifying 2 outputs. But your state variables are 4. You're going to find 4 first order differential equations. You should have an x1 prime, an x2 prime, an x3 prime, and an x4 prime that you find in problem number 3 of your homework. Then your output matrix H would be of what dimension? Is it 2 by 2? We're going to Home Depot. What are we going to buy? A 2 by 4. It has 2 rows and 4 columns. Because we had 4 state variables, it has to be compatible with that collection of variables. 2 outputs gives me 2 rows. 4 state variables, that gives me the 4 columns. In this case, I have 2 state variables. There's my 2 columns. And I have 1 output identified, y of n. And this now says, oh, that's 1, 0 for H. And J, a lot of times I might not even write it in. I might not even say plus 0r because it's not there. I might just say y is equal to hx. Now, here's maybe, don't confuse yourself with this, but now if I say system matrices, I'm referring to all 4 of those matrices. Phi, gamma, H, and J. If I just say the system matrix, that's phi. The system matrix possesses the dynamics of my system. How does it naturally like to move? Or I might say shake. If you now excited this or initialized this system, how would it naturally want to behave? And that's governed by phi, your system matrix. How that system is interconnected with the environment will depend on gamma and H and J. And those then are your system matrices. How do you inject information in and how do you extract information out of this system depends on your input matrix and your output matrix and the direct feed-through matrix, which this is now the output matrix. Here's your direct feed-through matrix, and those 4 taken together are your system matrices. What we want to do now is convince ourselves that the eigenvalues, and I'm assuming you've had some linear algebra, you can find eigenvalues of a matrix. The eigenvalues of phi, that's our system matrix, in this case equal -1 and -2. That's for this example. Generically, no. Phi is going to have wherever its eigenvalues are. That's why I'm saying in parentheses for this example. And those correspond to the roots of the characteristic equation, or how the system is naturally going to shake or evolve relative to initial conditions. We can convince ourselves of that by looking at the determinant. That's what these vertical bars mean, the determinant of lambda I minus phi. Set that polynomial in terms of lambda equal to 0, solve it for lambda, and we better get lambdas equal to -1 and -2. Let's do that. We now have lambda I minus phi. What's the size of I? My I, it's about 3. The I is 2 by 2, isn't it? So in this case, we have lambda times a 2 by 2 identity minus our system matrix, or that now if you put everything together, we have Lambda's on the diagonal, and we're subtracting the phi matrix from that. We now have a 2 by 2 matrix. Lambda minus 1 in the top row, 2 lambda plus 3 in the bottom row. We can now find the determinant of that 2 by 2. That's the product of the diagonal terms, or elements, minus the product of the off diagonal. And this is our characteristic polynomial. And if we set that equal to 0, we have our characteristic equation. Or lambda squared plus 3 lambda plus 2 equals 0. There's our characteristic equation. And in fact, we've seen that already, which means we better remember how it factors. And we see that we have one of those eigenvalues of our system matrix equaling minus 1, and another value of lambda that causes that left-hand side to vanish is when lambda 2 is equal to minus 2. And because this is a difference equation that we've played with before, that's why it has the same roots of an earlier example.
So, to determine if a system is stable like we saw the last time, should we look at the gain, or should we look at these values of lambda?
Now the question was, if we are trying to find the stability of this system, what do we look at? You may not be able to see whether this system in the all delay block diagram form is directly stable or not. You can't just look at those coefficients. You have to plug those in to your state space representation and find the system matrix phi, which is here, and now find the eigenvalues of phi. The coefficients are there, but since this isn't a triangular or diagonal matrix, you can't immediately identify the eigenvalues of that phi matrix. Here, in fact, this is a canonical structure for phi, and it corresponds to a lambda squared plus 3 lambda plus 2. So you see the coefficients directly in that characteristic polynomial, but we need to find the roots of that characteristic equation and then see, are those roots inside the unit circle? Here it's not. This is an unstable system. So the question was, can we assess stability? Maybe if you have better powers than I do, you can from inspection of the block diagram, but generically you need to put it into a state space representation or a transfer function. You could now find the transfer function, find the poles or the roots of the denominator polynomial, and assess stability from that. And those will be different from just these coefficients. We've been in the time domain. Let's now go into the frequency domain. We want a block diagram in the frequency domain, and that means we want to replace the unit delays in the time domain with operators equaling z to the minus 1, where z is this complex frequency variable. And in fact, we can simply immediately copy down the same block diagram that we had. We now just need to erase the signals because they were in the time domain and replace the blocks with z to the minus 1 operators instead of unit delays. I'm going to quickly do that here. We have This is now R of Z. This was minus 3. And this was minus 2. And I now have my frequency domain block diagram, and I can label this. I could say, well, this is still my output. Let me call that Y of Z. And convention says that the outputs of these summing junctions sometimes are representative of error signals. Let me just denote this signal as E of Z. And now I want to make the point that we need to distinguish between apples and trees. Usually you say apples and oranges. You could do that too. But here I'm trying to distinguish between signals and systems, or signals and subsystems, when we're doing block diagram analysis. We now want to find the transfer function between the input R and the output Y. Is this problem 2 on the homework? Sort of. Now you just might be seeing, instead of simple Z to the minus 1 blocks, you might have a subsystem G sub 1 of Z sitting there. That's now a subsystem. We now need to make sure that we combine apples with apples and not apples and oranges, where the oranges are our systems or subsystems and our apples are our signals. We can't say 6 apples are equal to 5 apples plus a orange. That doesn't work. We have to be consistent on both sides of the equality sign. We have to be working with apples on both sides, or signals on both sides. And to produce maybe a little bit more straightforward analysis in this block diagram algebra, it's usually helpful to write your equations based on the output signals from summing junctions. Question?
You said one of the subsystems might consist of G1, G sub 1 of Z.
So now what the question was, you said one of these systems might be G1 of Z. I'm trying to relate it to your homework problem, and I'm saying in your homework, this particular block may be more general. It might be a G1 of Z and not just a basic Z to the minus 1. That's all I was saying. And this block could be an H of Z and not just a gain. But those still represent systems, the highlighted, are systems or subsystems or gains. They are not signals. So those were oranges, although maybe I should have called them lemons since I was using yellow. Apples and lemons. Okay? I still can't combine those. But to do my block diagram analysis, or algebra, I'm going to focus on writing the equations based on, okay, who knows what I'm trying to do here. Trying to fill in whatever. I want to write my equations in terms of signals coming out of my summing junction. So I want to write these equations maybe in terms of E of Z, as I've labeled it. I now have an E of Z, and I'm running out of power on my room battery. So microphone. So let me know when you can't hear me anymore, or you'll just fall asleep. Am I going low in the corner? Can you still hear me? Okay. So now I want E of Z. And I need to write E of Z as what? Is E of Z a signal or a system? That's a signal. All of these lines are signals. The blocks are subsystems or systems. E of z now is equal to many different things, but do you see that one of those, E of z is the output, everything else is an input. This is now R of z. And what else is it? Well, you might, for starters, say, well, it's then this one, which is, it's not just minus 2, is it? I can't say R of z minus 2 because minus 2 is a signal. I'm sorry, is a system. It's a lemon. I need it to be a signal. It needs to be this signal, which is minus 2 times y. What else do I need? I need one more. I've already accounted for that one and this one. I have one more signal to add in to make my output, and that's now minus 3. Do you see that I could now take this and say, okay, I want that signal, but I'm going to rewrite that signal as this with that and then that. It's not minus 3z to the minus 1, is it? That's 2 lemons, right? We have to have a signal being filtered through those lemons to give us a signal. And the system is minus 3z to the minus 1. Meaning now I have over here minus 3z to the minus 1 e of z. Are we comfortable with those, or with that equation? And in fact, what I really want to do is I want to rewrite this in terms of just 2 variables, an input variable and an output variable, where my output could be an error signal. Can I now get rid of that y? Can I rewrite that y in terms of e? So now do you see how I could now relate y with e? Y is now z to the minus 1 times z to the minus 1 e. Here, now I can say, oh, I'm going to replace that with z to the minus 1 times z to the minus 1 e. Or z to the minus 2 times e. I now can say that e is r of z minus 2 z to the minus 2 e of z minus 3 z e to the minus, or 3 z to the minus 1 e of z. Now I have one equation that only involves 2 signals, e and r. That's good, because now I can find the ratio of those 2 signals. Let me put the e terms on the left. I have a 1, I have a plus 2. Well, let me write it with increasing negative exponents. Let's say plus 3 z to the minus 1 plus 2 z to the minus 2 e of z is r of z. Now I can solve for e of z in terms of r of z. E of z is like an output. That's the signal coming out of the summing junction. I could view that as a signal that I'm interested in. That's now 1 over 1 plus 3z to the minus 1 plus 2z to the minus 2 r of z. Or I could even think of this as some system g sub e of z. That's the transfer function. That's the filter between my input r and that signal coming out of the summing junction, which I was calling e. G sub e of z is a subsystem. It's a filter. It could be it could have been as simple as just a number. What did I do? I have no idea what I just did, but somebody went. Okay, I can't. I should have learned my lesson. I should have stayed inside the unit circle. If you're listening to this, you didn't see anything happening, but the classroom went completely dark, meaning the screens were no longer visible. But we now can say that this subsystem, G sub E of Z, is now E of Z over R of Z, which is equal to 1 over 1 plus 3 Z to the minus 1 plus 2 Z to the minus 2. And the convention is usually to write these transfer functions in terms of positive powers of Z. In this class and in signal processing classes, sometimes you do keep things in terms of Z, powers of Z to the minus 1. But here, when we're talking about a system or a subsystem, we might want it in terms of positive powers of Z, and I can create that by multiplying by 1, where 1 is Z squared over Z squared. So that's the convention. The convention, typically when we're talking about subsystems or systems, is usually we write transfer functions in a controls class, maybe not in a signal processing class, but we usually write transfer functions in terms of positive exponents on Z. And in so doing, do you see now if I push that Z squared through the numerator and the Z squared through the denominator, I can now write G sub E of Z a little differently, but it's equivalent. It's now Z squared over Z squared plus 3Z plus 2. And that's still E of Z over R of Z. But maybe that's not the transfer function we wanted, what we wanted. Maybe what we wanted was the transfer function between R and Y, the input R and the output Y. But now that we have this, it's fairly clean to find the next transfer function. But here's one transfer function from that block diagram. If we want G of Z, which is now Y of Z, the output Z transform over the input Z transform, do you see how we might create that? We had a way, or we saw how to relate Y to E. Y was just Z to the minus 1 times Z to the minus 1 E of Z. Or Y was now Z to the minus 2 E of Z. And now we can use this relationship, or this relationship solved for E, to get rid of the E here and rewrite it in terms of Y. Meaning, Y of Z is now Z to the minus 2 times 1 over Z squared plus 3Z plus 2 R of Z. This was E of Z. So that now, well, not following along my notes. I'm freelancing. So this is the E of Z in terms of R of Z. Yes? Or we could have kept everything in terms of the z to the minus 1. It wouldn't have mattered. But this now tells us that y of z, the transfer function between r of z and y of z, we push that z to the minus 2 through, and we end up with 1 over z squared plus 3z plus 2 r of z. And this is our g of z. And this is our system's transfer function. Question? G sub e of z would be the transfer function between the input and that signal at the output of the summing junction. It may not represent anything meaningful, but it is a transfer function. G sub e of z, the question was, what is G sub e of z? That's an intermediate transfer function if you wanted to think of it. Maybe you didn't need that. Now you can just keep that on the side. You don't need to turn that in necessarily, but now you need G of z, and you can create it cleanly from G sub e of z. In some cases, G sub e of z could have been a transfer function that you wanted. You wanted to see what's that signal coming out of the summing junction relative to the input r. And if you go back to this block diagram, I hope that now you can see that E of z is not just R of z. E of z is a filtered version of R of z. And how it's filtered is through G sub E of z. It's now z squared over z squared plus 3z plus 2. Now we have a lot of these z's floating around, not meaning you guys are zing it at all, but let's see if we can understand a little bit more or get some more insight into this complex frequency z that's now in our transfer functions. Let's now talk about an interpretation of z. And what we're going to do to get some insight into z, let's rely on our insight that already exists with the Laplace transform complex variable s. Let's recall the Laplace transform. And in fact, the Laplace transform of a delay. So let's recall the Laplace transform and what a time delay what that looks like in the S domain. Suppose I now give you a generic signal x of t, and I want it in the frequency domain. You could say, well, just shift key, capitalize it. Capital X of s. But the definition of the Laplace transform, the one-sided Laplace transform, is this integral from t equals 0 to infinity of this time domain waveform x of t e to the minus st dt. That's where the capital X of s comes from. We simply do this complex exponential weighting of the time domain waveform x of t to produce the frequency content capital X of s. What if in the time domain I handed you a delayed version of x. This is now t sub 0 is our time delay. What does that look like when we take it into the frequency domain in terms of capital X of s? Do you remember the transform property? And you may not, but you'll remember it when I write it down. It's now some version of capital X of s. These are the same, but it's a complex exponential weighted capital X of s. This is now how the time delay in the time domain impacts the frequency domain expression. This is now the impact of the delay. That's kind of ugly. I don't know if I can clean it up anymore, but that was e to the minus t sub 0 s. Scaling capital X of s, which is the same as the Laplace transform of x of t. If we now delay x of t by t sub 0 units of time, then we simply weight capital X of s with this complex exponential e to the minus t sub 0 s. Now, we said that we were trying to relate Laplace s with z in the discrete time setting. And what do we know about z to the minus 1? How are we treating that? What did that correspond to? What did z to the minus 1 correspond to in the time domain? One sample period delay, wasn't it? Z to the minus 1. So let's now look at, in the continuous time, let's say if t sub 0 has a numerical value equal to one sample period. That is, t sub 0 is equal to capital T. Then what does this e to the minus t sub 0 s look like? Then a one sample period delay which we know in the z domain as z to the minus 1. What does that look like in the s domain? That's going to simply be e to the minus t sub 0 s when t sub 0 is equal to capital T. When the delay is one sample period. Or that says that this is now e to the minus ts. Or you might see me write this as e to the minus st. Sometimes it's cleaner to put the t. These are scalars. S is a complex number, but it's a scalar, and capital T is a scalar time. They commute. It's cleaner a lot of times to just write it as e to the minus st. That means then if we're comparing z domain and s domain, z to the minus 1 is now e to the minus st, where t is equal to a sample period. The units on that are seconds per sample. Capital T might be 100 milliseconds, or 0.1 seconds per sample. Every sample is occurring in 100 milliseconds of time. If z to the minus 1 equals e to the minus st, I hope you can see what z equals. I now have 1 over z is equal to 1 over e to the st. The numerators are the same. Now I can compare the denominators, which are z is equal to e to the st. There's my relationship between the z complex variable z and the complex frequency variable s. They're both complex frequency variables. This now corresponds to an advance in terms of an operator of 1 sample period. And in fact, this is our definition of the complex frequency variable z in terms of the complex frequency variable s, where z is a complex number that we will use as a frequency domain operator for discrete time systems. If we now know how to relate z and s, let's do some mapping. Let's now look at what happens if we looked at a point or regions in the complex s-plane. Where would they map to in the complex z-plane? We now have 2 complex planes. We have an s-plane and we have a z-plane. This is now the imaginary part of z. This is the real part of z. I'm sorry, of s. Imaginary of s, real of s. This is now the imaginary of z and the real of z. And suppose that somebody said, well, I have a point in the s-plane. That's now an x. Let's say that is now -3 plus j2. And I want to know where does that end up in the z-plane if we map it through this relationship. Where does it go? Does it go to -3 plus j2? No, because it's a little different in terms of it's not z is equal to s. It's z is equal to e to the st. So we have to have a sample period in combination with s and then use that in the exponent of e to determine where we end up in the z-plane. But we can sort of talk about that in general terms. We can now say, okay, my complex frequency variable s is some minus sigma plus j omega sub d. And in our case, we said it was -3 plus j2. Our damping was 3. We're -3 units into the complex s-plane, and we have a damped frequency, a DAMP-ED. Damped, I put a P in there, omega sub d, that's our damped frequency of oscillation. Now, if we use this relationship, we can now say, okay, z is e to the minus sigma plus j omega sub d times t. we can now distribute that sample period through the two terms in the exponent, and we now have z is equal to e to the minus sigma t plus j omega sub dt. We also know how to rewrite this using our knowledge of exponents. We have e to the linear combination of something in the exponent. We can split that into two terms where it's now a product of two pieces. The first piece we could say is e to the minus sigma t, and the next piece is e to the j omega sub dt. That's just applying our knowledge of exponents. What we will do now, though, z, we can visualize as a complex number that has a magnitude or a distance away from the origin of capital R, and if we combine these two terms into one new term, theta sub d, we now have an angle. Or, what I'm trying to say is that we can now rewrite z as r e to the j theta sub d, where r is equal to e to the minus sigma t. R represents our magnitude of this complex number z, and theta sub d, now realize that I'm calling it theta. Theta sub d is equal to our damped frequency of oscillation times the sample period t. This is actually an angle in the complex plane. Z is now, you can think of it as a magnitude at some angle, where the magnitude is R, and this angle is theta sub d, and that point is z. This is now our z plane. I give you an r and a theta d. You can pin that z somewhere in the plane. Let's now use that insight with our particular value that we started with. We started with s equaling minus 3 plus j2. And let's go ahead and let t be 0.04. And you may not know where that came from. You put on your hat that wants to ask the question, why? Let's just hold that question for now. Let's just assume that we're okay with a sample period of 40 milliseconds, 0.04. What does that mean? Let's now see where z goes. You know where s is in the complex s plane. Now we look at e to the minus 3 plus j2 times 0.04. This is now e to the minus 3 times 0.04. E to the j, 2 times 0.04 is 0.08. This is now e to the minus 0.12, e to the j 0.08. This has units of radians. If you wanted it in degrees, you could convert it to degrees, but e to the j theta sub d is 0.08 radians. This is now our r, that's the magnitude of z, and the angle is 8/100ths of a radian. And you could convert that to degrees. Z is now e to the minus 0.12. You can calculate that. That's a number. What's e to the 0? 1. What's e to the 1? 2.7 something, right? What's e to the minus 1? 1 over e, which is 0.37 roughly. So this should be a value that's less than 1. And it ends up being 0.887. And the 0.08 in degrees is not quite 5 degrees. It's e to the j 4.58. You can now sketch that. You can now say, oh, I'm over here at 0.887. That angle may not be very accurate, but this is 4.58 degrees. And you're maybe comparing that to 1. So the polar form of that z puts you there. This is now our z-plane. Location for where we started in the s-plane. It was in the left half plane. I may fill in some notes after class and try to make this connection a little bit more, or provide a little bit more insight into the s and the z mapping. But we've now done it for 1 point. And what did we do? We were in the left half plane, minus 3 plus j2. That would be stable in continuous time. Where did we end up relative to the unit circle? A magnitude of 0.887. We're inside the unit circle. Points in the left half plane in the s-plane map inside the unit circle in the z-plane. We'll pick up somewhere there next time.